All right, welcome back to Open Analysis Live. This is part two of a two-part Unpacker series that I'm doing. So if you haven't already watched part one, go back and check it out. At the end of part one, we were left with the first stage of the unpack binary called stage1.exe. So if we pop over to our IDA instance here, we can see we've already loaded up stage one. That we extracted in the first part of the series. We've loaded it up, and as you can see, I've already done, because this is more of a walkthrough than a live tutorial, I've already done a bit of analysis. I've already put in some labels and put in some breakpoints. But I really hate it when people skip steps. So what I'm going to do is I'm going to just show you how I determined, how to call these, how to label these functions, because there is a lot of dynamic API resolution here where so if we look at our imports, there's only two imports, create process and message box. So you can see that obviously they're going to be doing a lot of dynamic importing. And then if we pop back to the view, you can see I've already sort of labeled things like terminate process or create process. So I want to show you quickly how I did that, and then we'll fast forward and assume that you did that for all of them. So what we're looking at here is after I've already labeled the functions, and you can see here's kind of a trick that, like, I think everybody knows this, but I'll just mention it anyway. One of the things I like to do is if I don't know what a function is, like here I've just called this double garbage, more garbage. What I like to do is I just like to give important functions that I'm going to be looking at. I want to just give them some sort of string name that I can remember so that I can keep it separate from functions that I haven't already looked at. So this is like sort of like a more of like a malware triage thing where you don't really care too much about what's actually going on. Like you don't want to have to analyze all this crap. You just want to, sort of get to the important bits and take a look at those. So the way I do this is sort of just keep giving names to all these different functions. If they have like a call to, so here I'll just show you like the create process. If we see where that's referenced here. So you can see like create process is called in this function. So I just called the function, I just called it wrap create process. I don't really know if that's what it's doing. I'm just giving it a name so that it stands out when I'm looking at the assembly. It makes it a lot easier to read. So that's just like one of the tricks. I think everybody does this. I just wanted to mention it in case you're very new to reverse engineering. It's just a really helpful thing to do. So like I was saying before, there's no imports, and I had to go through it and manually let's go to start and manually figure out what all these imports were. I could have scripted it, but and I'll actually talk about that in a minute. But what I just want to show you how to do everything very simple and manual for the tutorial, just so you know like how it's done, manually before we get into like automating this stuff. So I'm also, just before we get into that, I also want to take a look at the sample that's been uploaded to Hybrid Analysis. So not my favorite sandbox, but since malware.com is down right now, we're going to use this. And I didn't want to use like my internal sandbox because I want something that you guys can actually have access to, so you can look at the same results that I'm looking at. So if we look at this, it was actually submitted as fun, but it's the same exe. So, if you don't trust me, I can show you hashes afterwards, but it is. So if we look down here at the processes that were spawned, we can see that when it was run, it spawns explorer.exe, and we can see that actually did run. So there's like some network traffic, some interesting strings maybe that were extracted. But really all we care about though is the API calls. So we can see that there is probably going to be some process injection into explorer.exe. So if you click on the process and you click on API calls, again, hybrid analysis is really a pig when it comes to this stuff. Like it's really not good. Cuckoo is significantly better for looking at API traces. but we make do with what we have. So what I'm going to do is I'm just going to show you at the end of this trace. So we go to the final API trace, and we can see terminate process, resume thread. And if you missed the part one of this tutorial, I just talked a little bit about process injection. So I'll just do a quick reminder here. When you're doing process injection, there's like a few different very common patterns that you'll see. Now, this sample is exciting because it doesn't follow those common templates, but it has some of the similar characteristics. So the two most common templates are to create a process suspended, then write process memory. So you write something into that process and then resume thread. So that's number one. That's the easiest, simplest way to inject into a process. The second way is to create process suspended, map a view of that process memory into your own process, write to that view, and then resume thread. So these are like the two most common ways that you'll see process injection done. And if we look here, we can see that resume thread. We can see some map and unmap view, right? So it looks like this one is following, it looks like this malware is following the second type of injection where they're using maps. But I'll show you as we get into this that it's actually much more complicated than that. So normally, if they're using maps, one of those map views is going to contain the PE file in it. So because, again, this is going to be difficult to follow if you're not really familiar with how processes are mapped in memory. But basically, a PE file will be mapped as a bunch of different segments in memory. So if you're using process injection, you need to inject those segments into the memory of the process that you're injecting into. So you can't just like load an entire PE in. So there's really two ways if you're using like map view of section. So one is to map view of the entire PE file, and then you just load those sections in wherever they need to fit inside the entire process. This is really easy to extract the injected PE file from, because you'll have the whole map, right? So you'll have like one memory segment that has the entire PE file in it. Another much more common way is to have a map for each section in the PE file. So if there's like a text section, data section, R data, whatever, you're going to have that many maps. And so for those, it's a little bit more complicated because then you have to extract each section. So you might have to extract like 4 or 5 different sections, and you need to recombine them into the PE file. So again, if you're not super familiar with how that works, you just look up like process injection. There's a million tutorials that are way more interesting than my bald head talking. So go check those out. But basically, in this scenario, they're using a bit of that technique, but I'll show you it's definitely not what you think. So so basically with that, we're going to dive in. We know that these are these API calls, like the map view section, create section, resume thread, create process. These are all API calls that we want to hook, right? So that's kind of like we go from the sandbox to IDA. That's kind of what we want to be doing. So so again, that's why I'm trying to resolve these APIs so I can find out where I want to hook. So here, what I'm going to do is I'm going to walk you through just one of the APIs that I resolved manually. So let's pick this query information process. So if we take a look at the function here, let's assume that I didn't know that it was query information process. So when I was doing this the first time, I would like look at the function. There's not a lot here. I don't really want to dig into anything, but I do see at the end of it this jump EAX. So anytime you see like a control flow change to like through like a jump EAX or a call EAX, something like that, it's always going to be of interest to you because that's not normally how you would change like control flow, right? You're not generally going to be jumping to an address saved in a register. You see this a lot in malware where these jumps are either going to be like silly stuff that they're doing where they're jumping to like unpack code, or they're going to be jumping to dynamically resolved APIs. So what I'm going to do is I'm going to throw a breakpoint on here, and then I'm just going to run through. I'm going to run it in the debugger until I get to that EAX. And then at that point, I'm just going to check and see what it actually calls, right? So what EAX points to. So let's do that now. We'll just hop over here. I do have a few other breakpoints set, so I'm just going to have to jump through those. Okay, so now we get to jump EAX, right? So let's just hover over here. We can see IDE actually has labels already pre-populated. So you can see here EAX points to NT-query information process. So we can see, okay, this whole function, it looks like, since that's the last argument, right? So it looks like this whole function is just a big wrapper to dynamically call NT-query information process. So then we can just label it like this. Now, so I'll stop running now, and I'll remove that debugger breakpoint. So now what we can do is if we go back to where this was called from and start, we can start looking at all these different functions. So if we let's say look at create heap, we can see, oh, this is actually not as good an example. It's a little bit messy. There's a lot of like garbage code and like junk redirects and stuff like that in here, just to make it difficult to analyze. And I kind of don't want to go into that. Like you can waste a lot of time trying to figure out what these functions are, when really like we already know what this is doing from looking at the sandbox run, right? We already know that it's going to do a create process, and then it's going to inject something into that process using map view section. So we've already seen that in the API trace. So there's not a lot of point in trying to figure out what all this crap does. All we really want to do is just hook those calls and call it a day, right? So so basically what we want to do is we want to roll through all of these different functions and see any functions that have this like, oh, here we go, here's a call EAX, right? Or any of them that have like a jump EAX. Just put breakpoints there, run in the debugger, and then relabel the function with whatever API call was called out to. Now, so again, I've already done that, and to save time, I'm not going to go through it. This is actually going to be a long tutorial anyway, so I don't want to waste time doing that. But at least now you know how to do it. And one thing I would suggest is, because we know from, if we hop over to hybrid analysis here, and we look at that API trace again. So because we know that at the very last traces before that process is resumed is going to be an NT-resume thread, what I would suggest is while you're going through and labeling the code, because you don't really know what it's doing yet, right? You're just running through it in order to label it. I would suggest putting a breakpoint on NT-resume thread. And then that way, if you ever get there, you can just stop debugging, right? And restart over again, because you never want to, you don't want to actually execute the injected process, right? So the injected process is going to be started in suspended mode anyway, and the only way that it resumes is if somebody calls resume thread on it. So all you have to do is put a breakpoint on like NT-resume thread in IDA. So if we again, if we start in the debugger and we pop over here into NTDLL and we go to NT-resume thread, where are we at here? Did I miss it? There we go. So if we go to NT-resume thread and we add a breakpoint here, we know that we're never going to get messed up, right? So we know that we're always going to hit that breakpoint before the injected process resumes. So we're pretty safe to just run the debugger at will, and we're going to be pretty safe, right? So that's kind of like the trick I would say to use if you if you want to start labeling the code with the debugger live. It is pretty fast. Like I mentioned before, there is a way to script this, because it's like going to be a call EAX or a jump EAX. You can actually just write an IDA script to put breakpoints on all of those opcodes. and do it that way. But I don't want to, I really want to focus on like the manual portion of this analysis so that you guys get, how it's like done basically all the steps. And then you can go ahead and script it up if you want to. Okay, so if we go back here, let's jump back to start. Oh, right. Stop, please. Are we at our start function here? Yep. So as we go through and sort of read the code here, we can see we're going to start to see some familiar stuff. I don't really care about the create process anymore. I'll just delete that breakpoint, and I think I have a breakpoint in create process as well. Yeah, I'll just delete that. Okay, so I don't really care about create process. What I care about are those create section and map view of section, right? Because like I was saying before, that's how you get your code into another process. That's how you inject your code, or at least that's what it looks like from the API trace in the sandbox. So here you can see I've put a couple breakpoints on reprocess memory, and I will take just a minute to explain how this works. So obviously, when you first attach to a process, so then when you first create a process suspended, you don't know anything about that process. So in order to get information such as like where the image base address is, just information generally about the process, you need to get the process environment block, the PEB. And so that's what you'll usually see with process injection. You'll usually see a read process memory from the process where the PEB is, and then they'll parse the PEB manually with like pointer math, in the code. So I did put, I was actually confirming this before, but again, it's not particularly important for this tutorial. So I'm just going to remove those breakpoints. So what's going to be important to us, again, delete that breakpoint. What's going to be important to us is these create sections. So I'll add a breakpoint to create section, map view of section, create section. I'll add another breakpoint here, map view of section. Now I've already gone ahead and cheated a little bit, and I have a pointer to a data segment inside this PE file. And so like if we jump there, we can see it's actually the R data segment. And if you want to know how I did this, basically if you look at IDA at this, like, I'm not sure what this is called actually, but it's like a map of like the memory of the PE, and it's color coded. So if you're not familiar with how this works in IDA, see the little arrow that's pointing to like where you are in the code, so you can move around. Everything that's blue is like analyzed like code data, right? So it's code. Things that are, well, here actually here's the color map right here. So we have data unexplored is stuff that they haven't, that hasn't been analyzed. And you have like instruction data here, but really when we see these big blocks of like this greenish yellow color, that usually means like, and we see that there's only a tiny bit of function code here. So that usually means that this is packed, and this is the packed section in the PE. That's generally, like, if you look at like packers that are just tiny stubs for the packer and then a big executable embedded in it, this is kind of the layout that you would usually see. Just a tiny bit of blue and then this big like greenish yellow blob here. So all I did was I just popped over to the beginning of the greenish yellow blob, and it's the R data section, and I just put a label here called compressed data. I just assume that it's going to be compressed data because it's, this is a packer and this is a big blob of data, and we can see that it's referenced in the code. So I put a breakpoint here. We can actually remove it now. It's not particularly interesting for this tutorial, but it is, it's something that like I would normally want a breakpoint there, and that I kind of want to watch what actually happens to that code, to that data during these routines, just to see if it's actually unpacked in place. So again, this is kind of like a trick that you might get more familiar with the more packers that you look at. But in this case, it's not really super relevant to what we're doing. So we'll scroll down here. Here's another map view of section. Keep scrolling down. An unmapped view of section. I'll talk about that in a minute. A map view of section, and then resume thread. So if we look here at all of our breakpoints, it looks like we've been able to put breakpoints for all of these. For all of these API calls that we can see in the sandbox trace. So it looks like we managed to grab all of them. You can even see that they're in order in that they appear here. So it means that we got the right ones. So I did say I'm going to talk about unmapped view of section. So if you're going to map if you're going to map code from your process into another process that you're injecting into, and it already has code in that section, you're going to need to unmap that code. So a lot of the time you'll see an unmapped view section of a remote process, so the process that you're going to inject into, and then a map view of that segment into your process, so you can actually write code to it. So that's why this is important to see this unmapped view of section here. And again, like I was saying, we have it grabbed in IDA with a nice breakpoint here. So where are we? So before we can make sense out of this, we just need to go over some basics with section mapping. So in order to use like map view of section to write code from your process into another process, each section will need to have two mappings, right? One mapping into the remote process where you want to write the code, and one mapping into your own process where you're actually writing the code, right? So you'll write it into a memory segment in your own process, which is mapped to a segment in the other process. So one section, two mappings, one remote, one local, okay? And it's kind of confusing to like keep track of this. So what I'm gonna do is I'm gonna just, I'm gonna have a notepad here, and I'm gonna just sort of set this up so I have the section handle. So I'll do like a section handle, and then I'll do a remote address, and I'll do a local address. So we can sort of keep things, clear as we go through and step through the code. The other thing I want to do is I want to talk a little bit about the actual arguments that are passed to map view of section. So let's do a map view section. So for those of you who aren't familiar with Microsoft internals, Windows internals, the ZW function is just another entry point for NT functions. So we can look at, and NT functions aren't documented by Microsoft, but ZW ones are. ZW ones are used for like kernel programming, whereas we're in user land looking at the NT interface for NTDLL. So these arguments here are going to be the same for NT map view of section, the same for ZW map view of section, or at least the same for these important ones that we're going to talk about here. So for the first argument is going to be section handle. So this is the actual handle to the section that you've created. The second one's going to be the process handle. So the handle to the process that you're going to be doing the mapping from. Now, again, if you're not familiar with Windows internals, invalid handle or like a null handle is going to be -1 or all Fs, and that means your own process, right? So if you have like a process handle that's all Fs or -1, it means, use my own process. Don't use another process. And then we have the base address, and the rest of this we'll worry about in a bit. But the first three arguments are the most important. And of course, the base address, if you're mapping from a remote process, is going to be the address in that remote process. And if you're mapping in your own process, it's going to be the address in your own process. So that's basically all there is to it. Let's pull up my notepad again here. And we'll pop over to IDA and we'll start debugging. And every time I hit create process or create section, sorry, and map view section, I'll take a note in the notepad. Now, the goal of this is going to be at the end, if we look down, we keep on following these all the way down until resume thread. So there's going to be a final map view section here. And what we want to do is we want to take a look at the data that's in that final map view section and see whether that contains the unpacked PE file. So this is like a trick. Again, we're trying to do this fast because, again, trust me, there's a lot more stages here. So we're trying to do this quickly to see whether we can just extract the injected PE file, being kind of lazy with just a couple API hooks. So without further ado, let's get into it. Again, every time we have a create section, okay, so let's pop over create section and let's find out what the handle was for that. Now, I'm not particularly interested about the actual section until it's mapped. So let's pop down until we get to the first mapping here. All right, now I'm interested. So if we look here at the arguments on the stack, so the section handle is 48. It's a local process mapping, and the address here, let's copy this here. And let's take a look at the address. All right, nothing in that address. So let's jump over it. Okay, so we have mapped this address here from our own process to handle 48. So let's mark that down. So section handle is 48, and we're at local address A4000. Okay, so let's continue on now. And if you missed what I did there, all I'm doing here is I'm just looking at the value of the pointer on the stack for the base address. So that's why I opened another window here to take a look at it. So let's continue on. Here's another create section, which again, I don't really care too much about the create sections until I start mapping them. So let's get to map view section. All right, here it looks like it's another section, handle 44, again, a local mapping. And let's step over it and see what the address was that was mapped. So here's the pointer on the stack. Copy that, and then let's go take a look at it. Go V D. Okay, so we've mapped this address locally, and so that's 44, and it was local, and the local address was 8B000. So this is pretty tedious, pretty tedious work, and I do apologize. We do have to do a couple more of these, but you'll see in the end, this is definitely where it's at. So here we can see there's a remote process. So we can see the process handle is 54, so it's no longer a local process. The section is 44. And the address that we want to be mapped at, let's take a look here. All right, let's pop over this. And let's take a look here. So the remote address is 9 and 4 zeros. And it's to section 44. So section 44 remote address is 9 and 4 zeros. Okay. Now I'll keep going. And I have a unmapped view of section. So I think I might have already mentioned this, but if you are going to map your code into another process, you need to unmap the code that's already there. So sometimes you'll see an unmap view of process that just simply unmaps a bunch of code that's already there, not for like uh, a section that doesn't exist. This is just basically a way of clearing code out of the process that you're going to inject into. But it's also used to unmap views of sections that we've been using before. So what's important here is we want to check the handle and make sure that we're not unmapping a view that we've already mapped. So let's take a look here at the unmap view of section. And yeah, sure, let's just look at there should be like a ZW version of this. Just like I said, so there's the process handle and the base address. So these are like the two arguments. So let's go back and we'll take a look and see the process handle. Why are things a little messed up here? I think there's a bunch of extra stuff on the stack here that maybe it gets popped off. Yeah, I think there's a bunch of stuff that gets popped off in this function. So but what we're actually looking for here is we can see that the process handle is 54, which we know is the remote process, and the base address that's being unmapped is this big sucker right here. So let's pop back over to our notepad, and I'm just going to mark down unmap remote process. Okay. So what that's doing is that's clearing out a code segment in the remote process. So now let's go down to this last map view of section. Okay, interesting. We have it's going to be for section 48, and it's going to be in the remote process. And let's take a look here. Go to this address and take a look at it. So it's going to be at that address that we just unmapped. So let's go back and look at our notepad, and I'll explain the whole picture of what's just happened here. So keep in mind that it's remote process, this giant address that we just unmapped, and it's section 48. So let's pop back to our notepad. Section 48 here, right? And it's being mapped into this address in the remote process, and it's going to be this local address. So let's take a look here at I'm sorry, I have to copy that address. Let's take a look at our code and see what's actually being mapped, right? So what's actually in our process that we're mapping into that address. Because again, that looks like an image-based address. This looks interesting to me, especially since we just unmapped it. So let's come over here and we'll go to that address and see. Oh, hey, look at that. It's a PE. So at this point, we can see, just to go back through it all, we are now mapping a PE into that process over where because it's explorer.exe, I know that that's the image-based address. So we're mapping at the image-based address. We're mapping a PE file into it. So this is kind of like I was explaining. This is very similar to that process I was talking about before, process injection, the second one where you use map view section to inject code in. So what we can do now is we can take a copy of this code that's being injected in, unmap it, and then take a look at it in IDA and see what it does. Now, there's one other thing I want to do because this is kind of interesting, and this is where things get a little bit tricky. So I'm going to pop back to our notepad, and you can see, remember, we also have another mapped section that's mapped in at 9 4/0 hex into the remote process. And it hasn't been unmapped, right? There was no unmap call for that. And if we look here, the next function call is resume thread. So they're going to actually execute that process with that map section mapped. So I'm going to take a copy of that section too, just in case. I want a copy of that just in case it's important and, for some reason. Generally, you would unmap it if it wasn't important, and then so you can clean it up. But for some reason, they're leaving it mapped into the process when they run. And I can tell you now that this is the trick, right? This is the key trick, and why this is difficult to unpack if you're just using, if you think of it as just a normal process injection, because there's a second step here. So without spoiling the fun, let me copy those two sections out, the one that has the PE in it, and then the other mystery one that's mapped at 9 4/0, and then we'll take a look at what they are. So first thing I'm going to do, like I did in the previous tutorial, I'm just going to go over to my hex view, and I'm just going to copy the hex bytes and save as a file. So first I'm going to go to this address here with the MZ, and I'm going to copy it out. Now, one of the things you might have noticed me doing before when I copied the data out was that I didn't seem to care about copying extra bytes at the end of the PE file, and that's because it doesn't really matter. As long as you get the bytes that are used in the PE file, you can append a bunch of junk data onto the end of it. So if you accidentally copy a bunch of an extra bit of a buffer, it doesn't really matter, because when the PE is actually mapped, that data will just be ignored. So all I'm doing now is I'm just scrolling down until I see the end of the buffer, at which then I know that I can stop copying at the end of the buffer. So I'm just oh, here we go. Looks like we hit the end pretty soon. There's a bunch of garbage here. I might have gone past it. Remember, I'm looking for that FEE unused memory segment here. It's just, I think I'm well over where I should be. One of the ways that I could have sort of done this a little bit better is I could have looked at the length of the section to be mapped, and I could have copied that out, but I didn't think about it at the time. I was too busy trying to explain everything as I go. So I'm just gonna, whatever, I'll just copy down to here and save the file. And it's gonna be a big file anyway, but we'll deal with that. So we're gonna call this stage2.exe. Actually, sorry, .bin, and I'm going to save it to the desktop. Okay, and then I'm going to go and copy off that stuff that was saved at 9. Go to that address. Nope, it's 9 4/0. Okay, what's going on here? Copy that. I'd like to go to this address, please. Frustrating. Okay, so the reason why that's being angry with me right now is I'm gonna put a label here, is I was in the wrong segment, so it's not able to jump properly. Sorry, I should explain this better. So the reason why I wasn't able to do that is because I was using the address of the memory address of the remote process stupidly. So it's actually the address that I want is this one right here, and so that should work for me now. And I'm just gonna jump over here, open this in a hex file, and go to this address. I copied the wrong one. This is very frustrating. Okay. All right, this should work for me. Okay. So here's all that data. We can see it's just a data blob here, but I'm going to copy it out anyway. I come down here to oops. Okay. It's just too quick with the mouse here. I'm going to do this a little bit slower. So I'm going to come down and I'm going to just grab everything out of this buffer as well, or out of this memory segment. Be a little bit faster here. Ooh. Is that the end of it? I think that might be the end of it, but I'll just grab a bunch more just in case. And again, I could have saved myself the hassle of this if I'd actually just checked the length of the section buffer. Just kind of dumb of me to not do that. Anyway, so I'm gonna grab this and save to file, and I'm gonna call this dump _9 1 2 3 4 .bin. Save that to desktop. Okay, so now I'm going to stop debugging, and I'm going to pop over to my victim VM, and I'm going to kill these explorer.exe suspended processes that have started. Not that they're not doing any harm, but I'm just going to kill them anyway, just to make everything nice and clean. Okay,